Okay, so let's continue the course and the final topic, which is the Roth stability criteria. Roth stability criteria. Okay. So you saw that for the example of two RLC circuit in series, so we had a fourth order system, and when you go to the robotic system, for example, you're going to have 18-degree of freedom system. So it's going to be hard to understand for which range of the parameters your system is stable. And even when you come to ME430 for the control class, you're going to see eventually that for which range of parameters your controller is stable even. Okay? Yeah. Yeah, it is the most recent is 12 degree of freedom means that your system is 24th order. If you linearize, which is not possible for robots, it's s to the power of 24. Okay, so now if your closed loop system y over x is a m s m plus a m minus 1 a of s m minus 1 plus a m minus 2 s m minus 2 plus a1 s plus a naught, which means that how many zeros you have? How many zeros you have? How many? How many zeros? M zeros. Because this is a equation in the order of m. That's right. So m zeros you have. And then if you have bn Sn plus Bn minus 1 Sn minus 1 plus Bn minus 2 Sn minus 2 plus B1S plus B naught. Okay. Yeah. Is the closed loop transfer function y over x. Closed loop transfer function. Okay. And you have how many poles? You have how many poles? N poles. That's right. N poles. Okay. So Roth stability criteria says, because remember that the denominator is the internal dynamics of the system and the numerator is the external dynamics of the system. So we have to evaluate the internal dynamics of the system to judge is stable or is not stable. Roth stability says you have two conditions to judge the stability of the system. One, all denom coefficients exist, means they are not zero, and are positive all denom coefficients exist and are positive, means b naught and bn1 minus 1 and forever all of them b naught, they are not zero, the first condition, and bn minus 1 and the B naught, they are positive. See what I'm saying? Example. Simple example. If y over x is 1 over s cubed as s squared plus 4, is this system stable or unstable? By looking at it. No, but based on whatever I taught today. What are the coefficients of denominator? Tell me. That we're going to type in MATLAB always. 1. Okay, tell me the rest. Okay, so is it stable or unstable? Read this. Stable or unstable? Okay, read again this, all of you. Stable or unstable? Yes. As a 0. I said none of them must be 0. None of them must be 0. So here you are missing the 0s. See, 0. One of the coefficient here is 0, guys. So it's unstable. Which in this case is marginally stable. Remember? Because it has numbers. No. Read this again. Read loudly, please. Okay. Now what do you see here? Okay, one of what is 0? So it means your system is good. Understand? Good? So another example is, for example, this y over x is 1 over s cubed plus 2s squared plus s minus 1. If the system is stable or unstable. Do we missing any coefficient? No, right? All the coefficients are here. 1, 2, 1, minus 1. All of them are positive? Yes. Here we go. See, even by looking at it, you're going to say, oh, my system is unstable. If I go to the MATLAB, okay, for continuing the topic, recording this. Okay, if I go to the MATLAB, you see that if I solve this equation, come on, seems x, you know that how to solve equation, that's right, in MATLAB. So you can solve, actually I'm going to say poles are double, solve, what was the equation? S cube x cube plus, can you read for me? Can you read the equation for me? Can you read the equation for me? Can you please read the equation for me?
X cubed plus 2x squared plus x minus 1.
Okay. See, it has one right hand side poles means that the system is unstable. Do you see that? So it says, and a pair of complex conjugate pole in the left hand side. So it says this, if you plot in the imaginary and the real, has one pole here and a pair of complex, so it means that your system is unstable. Now what about this? What about this? Y over x is 1 over s4 plus 10s squared plus 5 s cubed plus 5s squared plus 20s. Is the system still unstable?
Stable.
Why?
All positive numbers.
Any other comment? Look at it again, guys. Compare this with this term. Do we missing something? Yes, because you have a 0 here. There's no constant number. So this system is unstable. While looking at it even, okay? Not even going to the MATLAB. The proof, what is MATLAB? Why? The proof is here. I'm gonna say again, so read the equation for me. S4 10s cubed
5s squared.
5x squared plus x, that's right? Plus 20x?
Yes.
There we go. You see, your system has one of the poles, see, pole 1 and 1, at the origin. Your system has a pole on the origin, mean on the imaginary axis. So if I plot this, I say step, let me do that. If I say num is for third or fourth order system 0, 0, 0, 0, and 1, and then was 1, 10, 5, 20, 1, 10, 5, 20, and 0, because the last one is 0. So if I say step num and then, the system is ridiculous, man. It's unstable, increasing forever. That's right. If I continue the time, it's going to continue. So you see, you have pole on the imaginary and the origin, on the border of stability and instability. Okay. Now, what about this term, guys? Okay, another example is y over x is, now look at here, s cubed plus s squared plus 5s plus 15. Is this stable or unstable, guys? Stable. Based on whatever I thought is stable. Based on whatever I thought. But let's put a hold on this. All the coefficients exist and they are positive. Well, let me solve it. Okay. Let me solve it. 1, 1, 5, 15. If I go to the MATLAB, 1, 1, 5, 15. Oops! You have a pair of congruent poles on the right hand side. Your system is unstable, guys. Interesting, right? See? So it says, despite whatever Payman thought, your system has this configuration of the poles. Imaginary, real. Oh, sorry. This and this. Ooh. And this. So your system is not stable. Exactly, it's unstable. And you're gonna tell me why you taught us that it's stable. Because whatever I taught you as condition 1 is only a necessary condition, not sufficient. Only necessary condition, not sufficient condition for stability. So that's why I say 1, because means let us put a hold on this. I'm gonna be back with this. So let's go for the second condition of stability. 2. After checking number 1, you have to go with the 2. You have to make this table, guys. Sn minus 1, Sn minus 2 coming down, S naught. Put the lines here, and we're going to talk about that. Okay. The Sn, you have to say this. Olaf, look at here. You have to take coefficients of b, and let me change the color. Bn minus 2, Bn minus 4, Bn minus 6. So you're going to do this. In front of this, you're going to say Bn minus 2, Bn minus 4, Bn minus 6. These are the even numbers, and until you have all of them. In front of Sn minus 1, from the closed transfer function, you're going to take this Bn minus 1, Bn minus 3, Bn minus 5, that odd numbers. So you're going to have Bn minus 1, Bn minus 3, Bn minus 5, Bn minus 7, and this. The last line, you don't need to do anything. Just copy this B naught from here. Just copy B naught. Now you have to do some operation. You have to multiply this by this, minus this by this, divided by this. You're going to say Bn minus 1 in Bn minus 2 minus Bn minus 3 divided by Bn minus 1. Then you have to do this. This multiplied by this minus this multiplied by this, again divided by this. You're going to have Bn minus 1, Bn minus 4 minus Bn minus 5 divided by, again, Bn minus 1. And this continues. How? I'm not writing here, but it continues like this. This multiplied by this again, minus this multiplied by the first one, again divided by the first one. Now the next line. The next line, exactly what you have done previously, like this. Let me show the black. The first element multiplied by this, minus the first element multiplied by this, divided by this. Let me call this A, the whole of this A. So Sn minus 3, see, it's coming down. Gonna be A in Bn minus 3 minus, let me call this B, all of that B. B in Bn minus 1 divided by what? By again A. Now the next one, right? And it continues like this. And you come down all the way here until we reach here. I'm going to do some example right now from trivial to the rest. After doing this, after making this table, you have to select the first column. The first column. Here we go. Now I have to make a statement. Can I go to the next page? Please let me know if you're done. Are you done, guys? Yes? Hello? Everybody? Are you done? Yes? Hello? Oh, yes. Okay. So, the sufficient condition of stability is that the first column be positive and exist, means none of them must be zero. Okay, let's do that. Y over x, let's go back to this problem, is 1 over s cubed plus s squared plus 5s plus 15. Here we go. Based on the first condition, all the coefficients exist and are positive. Okay, first condition, bingo. Now you have to make this table. S cubed, s squared, s1, s to the power of 0. As I told you, the first two lines and the last line is from the polynomial. Last line gonna be 15. First line gonna be like this. This, nothing here. And second line gonna be this here. So we're gonna have 1, see 1, 5, and nothing is here, 0. And now here 1, 15, nothing is here, 0. Everybody understand what we have done? I'm just jumping to the odd and even coefficients. 1, 5, nothing here. 1, 15, nothing here. Now what I'm gonna do, I'm gonna multiply this by this, and I'm gonna multiply this by this, divided by 1. So it's gonna be 5 minus 15 divided by 5. Minus 10 divided by 5 is minus 2. Here we go. I said the condition of stability that you have to select the first column. Oh my God. You have to select the first column. All exist. 1, 1, minus 2, 15. But all they are positive? No. You have a minus 2 here. So your system is unstable. Now, add this. The number of sign change in the first column is the number of right hand poles. Okay, guys. From 1 to 1, no sign change. From 1 to minus 2, 1 sign change. From minus 2 to 15, 2 sign change. These days, you have 2 right hand poles. As we saw, it's correct. 2 right hand side poles. Everybody clear? Yes? Huh? Okay, guys? If you are done, I will move to the next example. Okay, next example is this. Y over x is 1 over s cubed plus s squared plus s plus. Is this. Okay. Well, let me change it to, because this is nonsense. Oh. S4 s cubed s squared 2s plus. S cubed s squared s1 and s naught. So 1 4 2 8, and here is 10. Okay, that's the system. Fourth order system. Okay, it's a fourth order system, and as you can see, it's like this. Okay, so what we're gonna do, we're gonna say 1, 4, 10, and we're gonna say 2, 8, and 0, right? So 1, 4, 10, 2, 8, nothing, 0. The next line gonna be 2 multiplied by 4 minus 8. Minus 8 is 0 divided by 2. 2 multiplied by 10 is how much? 20. Minus 0 divided by 2 is 10. Okay? Now, you see that you have one single 0 here. What you're gonna do, because this is an exception, you have to change this epsilon with 0 with epsilon. Why I do that? Guys, look at here. If I keep it at 0, okay, so let us do that. Gonna be 0 minus 20 divided by 0. What's the answer of this in mathematics? What's the answer of this? Answer of this is minus infinity. Means I don't know. That's right. There's not a number. So I'm gonna change it with the epsilon. Plus epsilon. Okay? So now you have 8 epsilon minus 20 divided by plus epsilon. This now makes sense. See? So it's gonna be negative number. At the end, gonna be negative number. It's gonna be, let me say, b a negative number. Now let us say, and here is 10. So let us say, here we go. This system is stable or unstable? Guys, positive, 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 positive. What is this? What is this? Hello? Guys, you are there? The system is stable, right? Right? System is stable? What? Guys, you don't see? Yeah, is unstable. Unstable. Okay? So you learn that is exception number 1. If one element in the column is 0, only 1. Change it with epsilon plus. Okay? To make this stable. So if you go to the MATLAB, you see that is 1, 2, 4, 8, 10. So if I solve this equation is 1, 2, 1, 2, 4, 8, 10. 4, 8, and 10. You see that you have a pair of complex conjugate poles in the right hand side and in the left hand side. So system is unstable. Okay? So where is that? So, and the number of the sign change, I told you, from positive to negative, from negative to positive. So here we go. Two right hand side poles. Guys, let us, here we go. This is unstable. Now another exception. Y over x is 1 over S5, S4, S cube, S square, S and the number plus, 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 plus. Now you have to make this table again. S5, S4, S cube, S square, S1, and the S0. Now you know that you have to take this from the denominator. That's why it's recording. Yeah. So I'm gonna put here 1 and also here 1, 1, 1. And I'm gonna put here 2, 2. And I'm gonna put here again 1. Let me figure out because I'm drawing with you. 1, 1, 2, 1. 1, 2, 1, 2. It's gonna be 1, 2, 1, 2. And 2. Here we go. So it's gonna be 1, 2, 2, 1, 2, 2, 1, 2, and 2. So you got here 1, 2, 2, 1, 2, and 2. Here we go. So this is fifth order system. So now let's go to the operation. 2 minus 2 divided by 0, divided by 1 is 0. 2 minus 2 divided by 1, see? 2 minus 2 is 0. So you stuck here, because after this you cannot do anything. Now you have a row of zeros, not one single in the first column. This is the second exception in the rule of stability criteria. What you're gonna do, you're gonna get an auxiliary, a helping term. What is that? You're gonna say PS. You're gonna make it auxiliary term. Guys, look at here. This S cube from here has a coefficient 2. So you're gonna write PS gonna be, look at here, 2S cube, okay, and the next one plus 2S, because they are jumping like that, like this. This is how you write that. Understand? So s cube is 2s cube plus 2s. Then you're gonna have the time derivative of that. dp over ds, s derivative. Gonna be 6s squared plus 2. Understand? Sorry guys, I'm stupid. I was thinking about different. Sorry guys, you have to look at this S4. S4 coefficients is 1, 2, these terms. 1, 2, and 2. So you have to write here exactly. S4 plus 2s squared plus 2. I mean this. The line above that, right? This. Now you have to say dp over ds gonna be 4s cubed plus 4s. Now you see this s cube emerged here. You're gonna replace the coefficients there instead of 4 and 4. Simple like that. Everyone understand? Yes. So you get the law about the 0 and 0. Write the coefficients based on as you developed 1 s power of 4 plus 2s squared plus s4 is plus 2. Then you have a derivative with respect to the s, 4s cubed plus 4s. Then you're going to replace these in the s cube. Now you can continue. 4 multiplied by 2 is 8. Minus 4, 4. 4 divided by 4 is 1. And here is 0, obviously. 4, 8 divided by 4, 2. Next line. 1 multiplied by 4 is 4. Minus 8 is minus 4. Divided by 1 is minus 4. And the last line is 2. Here we go. Everybody understand what I have done? Yes? Now you select the first column. Here we go. All exist. 1, 1, 4, 1, minus 4, 2. All of them are positive? All of them are positive? Yes? All of them are positive? Guys? Yes? Just look at the numbers from kindergarten. 1, 1, 4, 1, minus 4, 2. All of them are positive? Okay, so means your system is? Great. How many right-hand poles the system has? How many? No. Number of sign change. How many sign change you have? From plus 1 to minus 4, 1 sign change. From minus 4 to 2, 2 sign change. So you have 2 right-hand poles. The proof is MATLAB. Right? The proof is this 1, 1, 2, 2, 2, 2. So it's gonna 1, 1, S5, S4, 2, 2, and 2, and 2, right? 1, 1, 2, 2, 2, 1, 1, 2, 2, 2, 4. 1, 1, 2, 2, 2, 2. Here we go. You have two right-hand poles. The rest are on the left-hand side. Do you see that? Yes, guys? Huh? We have 5 poles because shift order system. 2 of them in the right-hand side. Understand, everyone? Yes? So we're going to continue this topic by determining the range of stability in the next class. Okay? Then I'm going to hit the motor root locus and we are done with the if I see that's suitable for this course. Okay? And hopefully next week we're going to finish the course. Okay? Understand, everyone?
Yep.
Thank you.